不是4小时，是6点还是看那个？
我是那发
那个什么消息。我看那什么沉默录制的沉默上打1G 的VG。
反正确实打不过，就是。
还没说呢。
你往那放点东西，它就不错。演技。
Hello guys. So today we are going to continue on the maximal size matching schedule. But before I start, I just want to talk a bit about the lab sessions. How are you doing, guys? Did you finish the lab? Did you do the plots? As expected, you compare them to the ones we see in the lecture. I'm not going to do the police, but it's up to you to do them. Okay? We're going to see, for example, PIM today, parallel alternative matching. You have it today. You might as well test it. This is all for your good for your product. And the sooner you start getting familiar with simulator, believe me, the better. This is what I can tell you. And I think you are grad students, so you don't need me to chase you what you have done and what you haven't, right? So I trust you with them. Today I'm going to put on the VLE with the civil email. I'm going to put the content of this week's lab, where there will be an exercise for you to do. I'm taking it that you will do your best to prepare also, so that we run faster. Okay? Is that okay? The third point I would like to mention is about the group projects. If you did not choose a project and the group members, please do so soon, because the deadline is upcoming. Okay? Anyway, so I'm going to start from where we stopped last week, more or less. I think we talked a bit about the PIM last week, right? Stop a little bit further, but it's alright to start. So PIM is one of the first algorithms, so it's based on having arbiters of the inputs and outputs. And basically PIM, what it does, it iterates 3 steps. All maximal size matching algorithms do 3 steps. And when they do 3 steps, they do them in parallel. Okay? So that request is happening in parallel at each input port. Parallel. The same happens for the grant. So at every input, there is a small circuit that's called the grant targeter. And every output to the grant inputs in parallel. We talked about this last week. I hope this is clear, folks. The simulator is implementing this very algorithm in the source code. It's called PIM. If you go under the directory algorithms in the simulator, you'll find PIM, and you'll find this thing. And you might as well see them how they are implemented code-wise. Then after the grant comes the accept phase. So once every grant arbiter grants to the output, it does it randomly because it's called parallel matching, so PIM works randomly. Then the accept inputs, now they would accept the offer. And mind you that every output grants at most 1 input, and every input accepts at most 1 output. So that there will be a bipartite match. And the accept phase also is done in parallel for every input. And it's done randomly. Is this clear how it works? And this is the animation of the algorithm, how it works. So this is called the requests, where the arrows are heading from the inputs to the outputs. The request phase is trying to capture what every input port contains. Is this clear how it works? Is it clear? Clear or very clear, or maybe clear? If it's not very clear, please stop. So, every input would send the request in parallel, here. So the parallelism comes from this, that when this input is checking its input queues, in this case in queues, input 3, input 4, and input 1 are doing the same thing in parallel. Once every input notifies each output for which it wishes to submit packets, it has queue itself. Then comes a phase that's called the grant phase. This is the grant phase, whereby normally here, next to each output here, there is a small circuit that's called the grant arbiter. That grant arbiter is a small circuit that out of n requests, it would grant 1. Okay? That's exactly what happened here. So for example, the grant arbiter sitting there, which is sitting here, looks to the received signals, the received requests, and it grants to one of them. Sends a grant. Now comes another phase, which is the last one. Okay, here it says random selection because parallel matching does it randomly. This selection is done randomly, but there are a number of algorithms, as you can see on that directory called algorithms on the symbol. There are lots of algorithms that they implement a different discipline. Then comes the accept phase here. The accept phase is called the match or the accept phase, whichever you call it. Okay, whichever you call it. And this accept phase is a result of this phase, whereby now the accept phase, it's up to, there are a number of arbiters here that they are called accept arbiters. And these accept arbiters, they do more or less the same what the grant arbiters are doing. They work in parallel, they don't look at each other, whereby each one of them, upon receiving grants, it will select one. In this case, it selects it randomly. Is it clear how it works? Very good. And as you can see in this case, so this grant phase, it resulted in 2 connections. Why? Because input 1 received only 1 grant, so accepted. Input 2 is a hot input, received many grants. It can accept at most 1. Why? Because it translates to the low memory requirements of the router, because it sends at most 1 packet out. And in this case, it so happened to randomly select the 4th one. Okay? I hope it's clear. These are some properties of the throughput of PIM. So it achieves 63% throughput with 1 iteration, and I think we described how. We described last week how, right? Do you remember why it's 63? You don't. Who does remember? Guys, please, let's make it interactive. Otherwise, I'm gonna sleep. Okay, I'm not going to talk to somebody else. Nobody remembers. Ah,
Probably cheese is not accepted.
sorry?
But the probably cheese, you need to take into consideration the rate cheese.
Of course, you have to take into consideration the probability. Yeah.
Of the members is got no accepted.
Because the second one.
Probability that an input remains not granted is 1 minus 1 over n. I asked you if you remember, you said no. Now your colleague is answering, you answer.
No, still no, I can't remember. Because I clarified, I mean the answer is the second one.
I think so. Are you asking me?
Yeah.
Ah, okay, now I'm answering you.
Yeah, that's me.
Yes, this is exactly the explanation. It's in front of you. That's why I said no.
Yeah, I can't understand.
And you're right. It's because of the probability. It's probabilistic calculation. That's why you find out. Because here it says this quantity converges to 63. Okay? And that's how it's found out which one iteration is 63. So the answer is in front of you guys, please. So how do you find out that? Exactly as your colleague was mentioning. So you basically here we are trying to calculate what is the probability that an input will submit. Okay, assuming uniform. Okay, so now the probability that an input will submit only when it gets a grant. Okay, so if it does not get grants, it will not submit most likely. But if it gets a grant, for sure it will submit. Like this input, it got a grant, it sent it back. This input got more than a grant, it sent it back. So it's about probability of being granted. If an input is granted, for sure it will submit. So therefore, we calculated the probability that an input will not be granted, and then we do 1 minus. So the probability that an input will not be granted, first of all, the probability of an input receiving a grant is 1 over n. So the probability of that input not receiving a grant from one output is 1 minus 1 over n. That is the probability of this input not being granted by that output. And if I would like to calculate the probability of this input not receiving grant from all outputs, it's 1 minus 1 over n times 1 to the n. That becomes this one. Now, the probability of the throughput or the likelihood of that input submitting, therefore, it's 1 minus the probability of not being granted, right? Which is this quantity. With large n, that's an approximation, that's exponential, e. That gives you 63. The details of this are in the paper that you are given on the reading list. Well, you say no. What do you mean by no?
I don't know.
No. You agree? Okay, please guys, make sure that you understand this.
Excuse me.
Yes, please.
It is in terms of the like values of
Again?
n. What do you mean by having like values? Is it in terms of the input, or you consider like the number of inputs in a particular port, or is the capacity of input within that?
Are you asking about what's n?
No, basically, yes, I'm asking what that value of n actually, because which converges to an exponential value. So
You're asking me too many questions. Let's start one by one. Are you asking me what is n? Or
I know
not?
what value, I know the value of n,
Sorry?
but I'm a bit confused
Confused about what? Yes.
in terms of how it converges to an exponential value.
Oh!
So does it actually like, do you mean like it's a kind of, do you consider an input capacity, or
No.
it's like,
Because, I'm sorry, the way you're asking me, you make it feel as it's too many questions. Are you asking me why this is converging to this?
yes,
Let's go one by one. Is this one of your questions? Okay, let me answer this and then we carry on. In math, approximatively speaking, this quantity 1 minus 1 over n to the n converges to 1 minus 1 over e as n goes to big value. This is math, this is not me, not networks. Do we agree on this? So, do you still have questions more than that? You wanted to ask what n is? N is the number of input ports or output ports. Does that answer your question?
Yeah, it answers. Yeah, sure,
But what? There is a but.
maybe I'm a bit confused because in terms of that statement. So, and if the value of n is what I know as the number of input ports, so is fine.
So it's fine now.
Yeah.
N is the number of ports of the router, and usually when we talk about routers, the number of inputs is equal to the number of outputs. And generally speaking, we're interested into routers with high number of input ports. And when we say high number of input ports, we are talking about 32 plus. So for example, if n is equal to 4 by 4 router, okay, this quantity will not be this. Will be a little higher, will be 75 maybe, personally. This quantity holds, as it says, for large n. Clear? And answering your colleague, the answer to all your questions are in that paper, High-Speed Scheduling for High-Speed Networks. That is about PIM. And they keep telling you, by the way, all I'm saying is recorded on audio, so that you don't accuse me of telling you this. Integral part of the module is that you read the papers. It's an integral, you may be asked the questions in the exam from the papers. I'm saying it enough times, so it's up to you. So this, what I'm trying to extract you, it's really in the paper. And if you read the paper, it's there. Plus the paper, reading the paper is a good exercise for you anyway. Okay? I mean, honestly guys, let's be honest about it. How many hours do you spend a week on this module? Honestly. Honestly. I mean, take me as your colleague sitting there. Let's have an honest discussion. How many hours? I bet you come here 2 hours, maybe you spend 5 minutes thinking about it in the whole week, maybe. Let's be honest. Okay, you spend 3 hours, let's be a little optimistic. Sorry?
I'm not ready to say it.
It's up to you, really. Okay, so why I'm mentioning this? Because you got private study hours. And that private study hours, it means you read the material and the accompanying material. I'm sorry to mention this, guys. Okay? So part of it is please read the papers that are associated. Because lots of details are there. And the lecture is not going to give you all the details. I'm trying to cover a bit of material. Okay? Anyway, this figure here talks about the implementation of PIM. So its input, this is the input that you get, and that's your output. The input is a state of the input queues, which is this one. In a 4x4, I will get 16 states. Why? Because I will get the state of the input queues, and every input queue, input port, has n values, right? So n by n, and that will give you the state in bits. And every queue will be represented with 1 bit saying, do I have traffic or I don't have traffic? If it has traffic, it means there is a signal saying there is a request. Clear? So this is the input of the algorithm, or of the circuit. This is the hardware circuit. Okay? And these state of the queues, they will represent the request phase, which is this one. This one is represented by this one. Then comes the grant. Now, every grant would hold at most n signals. Okay, the signals that are coming to this grant arbiter n, which is sitting here, it means it's coming from this one, it's coming from this one, it's coming from that one, and that one. Okay, is this clear? Unless you stop me, I will take it here. So, and every grant arbiter is implementing some circuit in there, it's called hardware randomizer, to pick 1 out of 10, and randomly send it back. Okay. Sorry. Now, when it picks one, it would signal which one it is, and send it to something that's called an accept. This is, in fact, an accept, which is also a request for the other iterations. But in fact, this is the accept arbiter. You may add their accept, please, not only request. It's also accept, which represents this one. And that accept arbiter will record the decision made by the arbiter. Clear? Okay. Another implementation is this one, and we talked about it this week. Similar to the previous one. Now, we wanted to look at the way this algorithm is working. What we have seen so far, it's with one iteration, it gives you 63% with one iteration. And that 63% is assuming that the traffic is uniform. Did we cover what the traffic types we are talking about? What does it mean by uniform traffic? Uniform traffic is traffic whereby the data coming in has the same likelihood to be distributed on all outputs, is uniformly distributed, which means when you have, let's say the arrival rate is lambda here, the likelihood of that packet coming is having the same probability to be queued here or here or here or here. That's what it means by uniform traffic. A non-uniform traffic is when there is an arrival rate coming, and usually when we talk about the rate, we talk about lambda, which is the rate, the way you simulate it in the simulator called utilization. Remember utilization in simulator? Between 0, 1 all the way to 1, 0, 1, 0, 2, 0, 3. Remember what you did in the simulator in the lab? The utilization minus u, that's the lambda. It goes from 0 to 1. And if you remember, when you simulated uniform traffic last week, when you did that input configuration file, you made minus u the same for everybody, right? That means uniform traffic, which means the likelihood, okay? So this algorithm gives you, what is it? What I said, 63% is for uniform traffic. If the traffic is non-uniform, that's different discussion. We'll talk about it. Here we're trying to talk about performance of PIM and there are a number of iterations. So now if it has 2 iterations, for example, or 3 iterations, because there is nobody that stops you from having more than 1 iteration when you are running an algorithm, okay? If you define your time slot, if you want your router to work slower, you may afford the algorithm to run more than 1 time, and that's called iteration. So this is, for example, your input graph, which is the request. In the first iteration, this is what will happen. These blue ones are grants, randomly happening. So random selection. So it so happened to be these 2 guys being granted, these 2 guys are ignored. Okay. And it resulted into 2 inputs being connected to 2 outputs. Now, if you have to run the algorithm for another iteration, that would mean you have to take out the matched inputs and outputs, the matched pairs out of the new request. So if you have to run this, another iteration of this, which means you should take out 2 and 4, these are out. 1 and 4 are out, so what's remaining? 2 and 3 here, and 3 and 1 there. Clear? And that's exactly what happens. So in the third one, so these have been taken already. So the third one will be this only, 3 and 2. Clear? So these are being taken out, as I said, in the second iteration. And basically you add this one. This is the new one. 3 to 2. After second iteration. Clear?
So what are the percentages? You put the 100% after the second iteration.
Very good question. Percentage of what? Throughput?
Yeah, the first
Probability?
one was, yeah, the first one was
63.
63. But what after the second iteration?
Very good question. A really very good question. I'll answer you now. Which is, I'll answer you the next slide. Important question. Here, I just wanted to talk about the input traffic, as I said, to evaluate algorithms. A typical traffic is the uniform one, but this is the very simplistic type of traffic. The very simplistic. Internet traffic is usually like this, either hotspot or diagonal traffic. Any sort. You may have a traffic that has the distribution of arriving traffic to the output is non-uniform, so it's any form. That's the real internet traffic, because router normally does not have a uniform traffic coming in, going to the same port. Over time, it's not. So this is a very simplistic case, the uniform traffic, whereby the likelihood of traffic coming to an input is uniformly distributed over outputs. It's not the case. But it's a simplistic one to test. There are plenty of others. Okay? So we usually use this type of traffic to test the performance of algorithms. Is it clear? Good. So now, we use this one to test PAM. Here. This is what the simulator will give you, the simulator that you are running now. This graph is taken from that simulator. We are simulating a 16 by 16 router and the uniform traffic. And this is the input load, what I told you to do. I hope you should be familiar with this graph now, right? Please, if you are not familiar, stop. And I hope you understand what latency in cells, there it says cells. Latency normally is time, right? So what is cells? Can anybody tell me? Cells, which means packets, yeah. Why? Sorry? Can I repeat the question? I said why the latency, it's why the unit of latency is packets, or cells, or time slot, basically. Yes, please.
Maybe it's the delayed packets that wait.
Sorry?
It's the delayed packets that wait to be matched to an output port.
No, I did not really understand. You mean the delayed packet in the queues?
Yeah. Because
I quite did not get it. So the delay is...
If there are two packets from different inputs,
Yes?
one needs to wait.
Yes.
That's why it cells, I think, because it's causing the latency for the packet.
Yeah, true. But why the unit is cells? I'm talking about the unit.
It's independent about the time, so we don't care about like the speed of the.
Because this is simulation. Absolutely true. Because it's simulation. And we calculate the delay as in the number of time slots. Time slots is the ticks that the simulator runs. Because what you see here is a running of the simulator, is one shot in the simulator. Is that what you meant, maybe?
Kind of.
It was different.
Yes.
Much more clear the way it's said. Yeah. So this shows you parallel iterative matching with one iteration. And that one is somewhere here. And that's absolutely 63%. This gives you FIFO that you are doing in the lab now. Mind you, you see here the delay is up to 100. I remember when you simulated the FIFO, some of you got 1,000 or something like that. So that's why when you do 1,000, you would see this as if it went beyond 58.6. So when you cut your axis here in the correct value, you would see that. You clear? And I seen some of you were asking me questions whereby they see something like this. I think I explained to some of you, but it's worth explaining to everybody. Can you see it here? Ah, it's a good idea. Very good. Some of you, they were simulating FIFO, which is this one. They saw it going like this. Yes. Why is it? I explained this to some of you. I forgot to who I explained it. Do you? Tell them why it's like that.
I think because after like around 60%,
Actually,
then the simulator runs onto the times out because it can't reach the
Yes.
limit.
Somewhere in the simulator, it gives you the simulation time. For you, you asked it to simulate for 500,000 time slots minus L, remember? So that's the duration of the simulation. now that 500,000 in terms of time, of real time, that's really nothing. That's maybe half a second. But in the simulator, the 500,000 time slots is the time that you would like to see your output. Now there is a flag in the simulator that says, if your algorithm is saturating, the switch end of the algorithm is saturated, which means it cannot produce better match, it cannot give you better results, and that is triggered by the number of packets queued, okay? The simulation will stop much earlier than the time you gave it, which means it's not sound result, which means practically speaking, your simulation is saturated at that point that you are given it. If you see what I'm saying. The simulation manual tells you this, if you look at it. I'm trying to address some of the questions. Okay? What else can we talk about here? This is another simulation that gives you PIM with different iterations. Now, all I'm saying, this one gives you first out PIM1, which means with one iteration. Now, if you look at the simulator tells you how many, the simulator, in the simulator you can configure it to simulate any algorithm of 1 iteration, 2 iterations, 100 iterations, whatever you like. That is given in the configuration file. Remember in the configuration file you say fabric crossbar and the scheduling FIFO? If you put scheduling PIM and then -N2, it means 2 iterations. -N4, it means 4 iterations. All of that is in the simulator manual. Okay, how to use it. So PIM with 4 iterations is just small instructions. When you go to the scheduling algorithm, you specify it's PIM, and then you put -N, whatever number of iterations, it will iterate it out. Okay. Now this very graph, you could very easily simulate it yourself and see these results on your computer. It will be a good exercise for you if you have time. You can do this and see these results yourself. Okay. Now, your colleague was asking me about the number of iterations you need. Good question. I must say that, forgive me, I made the mistake. Please, these two here, you take it off. It's not n squared, it's n. This is answering the question. It says the number of iterations to converge. This is what you asked me. Okay? The expected number of iterations to converge is log n. So PIM will produce no more matches after log n iterations. N is the number of inputs. So if you have a 16 by 16 router, how many iterations will you need to converge? Log 16. How much is that? 4. Okay, so 4 iterations. Now here I said take off the square, please. Is that clear? Now this is also important. You know what it says there? It says the expected number of unresolved connections after iteration I. You know what's the consequence of the first line? Consequence of the first line, it says PIM is expected to resolve 75% of the connections each iteration. If you do the math, you'll find. The number of connections is n, the resolved one. The unresolved one are n over 4. So the resolved one are 3n over 4. Is it clear? Take off the 2, please. It's no longer my responsibility. The number of connections, the total number is n. The unresolved ones are n over 4. So what is the number of the resolved one? 3n over 4, which means 75%. You may note it at your own words here. So in each iteration, expectedly, 75% of the connections are solved. Okay? So after 2 iterations, you'll find it 75 and multiply it by another 75. Okay? That are remaining. So in the first iteration, you'll find maybe 4 are left, second iteration will be 1 over 16. The other one is 1 over 64, and you go like that. That's why it converges by log n. I hope this is clear. These are more properties of PAM. I think we're going to run out of time today, but it's all right. It's okay. So it is a fair algorithm because it's random. Can achieve 100% throughput as a uniform traffic. It converges in log n iterations to maximal size matching. That's what we said from the previous slide. It has a poor performance. 63% is supposed to be poor performance with one iteration because of its inability to desynchronize the output pointer. Desynchronize is important word we'll talk about what it is. Big word there, it says it's not easy to build in hardware. It's not a very fast algorithm in hardware because it's hard to build the random arbiters in hardware, hardware randomizers they are called. The circuit, it has a logarithmic power. This is a hardware thing. Now this is again hardware also, so the way you implement it in hardware, the best iterative maximal size matching algorithm takes O n squared, we've seen this, log n, or parallel time steps log n. In hardware, because in hardware you can do things in parallel as I showed you here, maybe not so much here. Things are done in parallel. So in hardware you can implement it in faster, which means log n steps actually, hardware-wise. That's the hardware complexity. Now it says if the number of iterations is constant, then it can be implemented in constant time. Because here, log n is a function of the number of ports. So, but in hardware you would expect, in real hardware running, you would expect the worst case scenario time-wise. So this says actually, if you have a constant number of iterations, let's say you say I'm going to design PAM for 4 iterations, you can bound its time in hardware. Okay? Can be implemented in constant time. Okay? But it says its hardware design is not trivial because of these randomizers. It's not easy to design it in hardware. Okay? This is about PAM. Any questions about PAM? PAM is described now. You have it on the simulator. And I hope you understand it. I must tell you that PAM is the very first algorithm in this family. So after PAM, there were plenty of algorithms, but the contribution of this algorithm, it was the first one that came in. So it opened up the eyes of people to the parallelism, if you see what I mean. Before PAM, nobody maybe seen this story of request grant accept. People, they were thinking about the matching in a different way. You see what I mean? And this is the very contribution of this paper, of this algorithm. But actually, it opened up a complete area about parallel iterative matching. After PAM, maybe there were 300 algorithms. And maybe 100 of them were implemented into real products. And maybe all of them, they were better than PAM. But PAM is the father. You see? So that's why it's very important. Okay? We will see a number of algorithms that they came after PAM, and of course, people try to improve upon it. But really, the big contribution of these guys, the way that they opened up the area. So one of them is called round-robin matching. Now, all of a sudden, people, they start thinking smartly, oh, why do I do it randomly? I will try to do it better than randomly, and a family of different algorithms have been proposed. The very simple of them is RRM, which is round-robin matching. And basically, round-robin, it's exactly PAM, except instead of picking randomly, remember that the grant arbiters, they pick randomly? Right? And the accept, they pick randomly now? This guy says, no, I'm not going to pick randomly. I will pick in a round-robin fashion. Each time I pick one, like the watch. So today I pick this one, next time I pick start from this one, and they turn over. Clear? So this is what it says here. Round-robin matching is easier to implement than PAM because of the, you will see that the way you implement the round-robin display is an easy way. You can use what is called the priority encoders in hardware, and it's easy. Okay? it says in terms of designing IO orbitals. IO orbitals, it means the grant and the accept orbitals. These are the IO orbitals. The pointers of the orbitals move in straightforward way. Now pointers. Now we are talking about pointers. Pointers. The pointer, it means the highest priority in a round robin. Do you know how round robin discipline works? Round robin, when you are, I'm sure most of you, all of you are international students, so you came through the custom, right? When you entered UK, right? A good way of round robin, the guy who stamps your passport, there are many rows in front of him. So round robin, he will ask that guy to come in, stamp the passport, then the next row, the next row, and then he goes back there. It's called round robin. Did you understand what round robin? Can't be any better than this. Okay. Round robin display. Round robin, you have normally it's a circular, the way you represent it. So you have a number of queues. Let's say they guys, can you see what I do here or here? Good. So if you have an input port like what I showed you before, input port number 2 that has 4 queues, right? These are VQs, so this is VQ, let's say, I don't know. This is input 2, so this is VQ2, 4, right? This one, right? This one is VQ22, right? Now, if I will have to implement a round robin here, I could represent a round robin like a circle, 1, 2, 3, 4, whereby there is a pointer, and this pointer moves, and that's the round robin. When I pick a guy from row number 1, it means I'm pointing to row number 1. Next time, I move here and pick a guy from here. This is my highest priority. And each time I serve one, it's a service display. And I go back. When I serve the 4th row, I go back to the 1st row, right? So when it reaches 4, then it keeps moving. It moves back to number 1. This is a round robin. Is it clear how it is? Very simple. Ah.
So what are 1, 2, 3, 4? Is that Q or queues?
The indexes of the queues. Yes. Okay, we'll explain in more details. So the request is like before, okay? The grant. Before it used to be random in PIM. Now it's not random, it's based on this round robin I showed you. It says if an output receives any requests, it chooses the one that appears next in a fixed round robin schedule, starting from the highest priority point. The highest priority point is this guy that moves. This is the highest priority point. This. So starting from where it stops last time, it starts from there, and that's the highest priority position. Round robin schedule starting from the highest priority element. The highest priority element is the element at which position the arbiter is pointing. So if in this time slot, the arbiter picks queue number 2, next time slot, it starts from this queue and move on. That's exactly what it says. If an output receives any requests, it chooses the one that appears next in a fixed round robin, starting from the highest priority element. The output notifies each input whether or not the request was granted. The pointer, this pointer, GI, this is called GI, the pointer, to the highest priority element, of the round robin schedule is incremented modulo n. Why modulo n? Because it circulates, if it increments without modulo, after 4 it will go to 5. So in order to force it to go back to 1, you make it modulo. Is it clear? So that's circular. Like when we say the watch is +1, the hour, this one. It goes from 1 to, it gets incremented modulo how much? Modulo 12, right? Because in each 12 turns, it goes back. So the modulo is 12. Okay? So to one location beyond the granted one, if no request is received, the pointer stays in its place. The key point of round robin is about how to move that point. We will see that plenty of algorithms have been proposed. Their difference, the main key difference, is in that arrow, how to move the highest priority point. That's very important, how to move it, in order to provide better performance. Okay? The accept is exactly like the grant, whereby at the accept side is not random again, it's exactly round robin. It's done in the round robin fashion. The text is quite long, but it's exactly the same story. So the accept, if an input receives any grant, accepts the one that appears next in a fixed round robin schedule starting from the highest priority element. And the pointer accept I, the A means accept AI to the highest priority element of the round robin schedule is increment modulo n to one location beyond the accepted one. If no grants are received, the pointer stays in its place. It's exactly like the grant, except it's called accept grant. Okay? It works like this. So assume we have a 4x4 round. This is how it works. Okay? In the case of 4x4, this is the requests. Okay? Now comes the grant phase. Oh, new stuff appeared here. This is the grant arbiter. Now we are talking about round robin. It's not random selection. And what's shown here is exactly, this is the round robin you would like to choose from, and this is the highest priority element point. Is this clear here? And this exists per output. This is called the grant arbiter. So output 1 also have the same story here. I'm not showing it. Output 2 has the same thing. And output 3 has the same thing. Every output, every grant arbiter has this structure, whereby it's a round robin arbiter with a highest priority pointer. And the highest priority pointer, this one, you know what it says? It says this one is instructing this output to grant the inputs starting from its hottest input. In this case, this is pointing to an input. This says, this is telling this output, if you receive grants from the inputs, please give priority to input 0 first. Start from 0 and move on. If you don't receive from 0, please try 1. If you don't receive from 1, move to 2 until you grant 1. So this is the order. Is it clear? The priority order. And the same for the rest. Is this clear? To be honest, I think it's very clear. Now, this is how the grant happens. It's no longer random, it's like this. The accept phase, which is after this one, is exactly like the grant phase. But let's continue now because this is an animation. So this arbiter, which input will it grant in this case? Can you tell me, guys? Will it grant that one? 0. This one will it grant 3. Which one?
2.
Because it starts from here, it does not find a request, so it will grant 2. That's precisely correct, guys. You got it right. Now, let me see. Why this move here? Because it granted 2. You're right. And this guy granted 0. It should move to 1. Hello. Move, please. Yes. Move to 1. So it grants and moves. Because the algorithm says here, if you read the algorithm, what it says, very important, the pointer gi to the highest priority, the move of the arbiter comes from this sentence. The pointer gi to the highest priority element of the round robin schedule is incremented. So it grants and then increments. Is it clear? Guys, what I'm telling you is very important. Have you seen this sentence? This sentence instructs the arbiter how it works. It says grant and then move to the next. Right? Remember this sentence. It's very nice sentence. So, it granted and moved.
This one. So, well, the animation is a little bit different, but actually what happens, it did the grant and then move. The same happens here, the grant and then move. And then the other ones, they do the same. I'm not showing you, okay? So the grant arbiters, they do the grant and then they move the pointers, right? I must remind you that all of these guys are done in parallel. They don't talk to each other. Okay, that's why it's fast. And that's why it's called parallel. Yeah? Why these guys have moved? No. No, actually it's correct. Because it gets incremented beyond. Okay? Actually, the first move, it says I'm granting number 2, and then it moves the one. Because it moves to the beyond the granted one position. Okay? So from which it should start next time. Okay? Now comes the accept phase. Remember that this animation is not clear, guys. Can you see? No, because there is a grant here. The grants are no longer shown. They are the grants here. Oh man, on my on the computer it shows, but here it's not. Here there is a grant coming from this, and there is a grant coming from there. It's not shown there. Is it shown on your one?
Yeah, it's there, but it's very low. It's what?
Sorry?
It's there. I can see it. It's very
Ah, you can see it's there.
It is, yeah, it is money.
There is
Oh,
from 1
It is
to
there,
2.
it is
and
3. So
Sorry?
definition.
There's one from 1 to, I think there's one from 1 to 2, and then there's 2 to 3 and 2 to 1. You can see it's very
You have to
light.
change the color.
Huh? I can. Okay, the point is you can see, right? If you can see, that's the
It's
point.
very light.
It's very light, yeah, maybe because of the variety. Anyhow, guys, I'll do it this way. I'll do it this way to simplify. Sorry? So basically, it is saying that this has granted this one, and there is a grant coming from here, right? And man, really I cannot see, I will follow here. Yes, and 2 has 2 grants coming, one from this guy and one from here. This is it. Okay? Now, the round robin, this is what it did. The grant phase gave this. Now the accept phase is exactly similar to the grant. The accept phase is based on priority pointers, exactly the same as before. Whereby, actually it says here, if you read here, forget this animation, go back. Yeah, this is the grant. Put this down. The accept phase, which I'm going to show you. If an input receives a grant, it accepts the one that please read from the page, from your slide then. We are going to talk about this now. Okay? It's exactly as the grant. Let me make sure. Oh man, it's very good like this. This is the accept now. Oops, cinema. The accept, starting from the highest priority pointer, please pick the next grant, accept it, and then move the pointer. That's what it says in your text. I remember it by heart. The question here, when you have more than one grant. When you do have more than one grant, you do exactly the same story. Starting from the highest priority pointer, pick the next, and increment. In this case, this arbiter, or this input, is receiving grant from input 1 and input 3. It's pointing at 0, it will pick one, and then it gets incremented to 0. So the one that is chosen is number 1. Depends on the move of the pointer. Okay? Because now I put it that it's moving this way, as you can see. So it could have moved this way also, but it depends on you. It could be moving clockwise or counterclockwise. That's the way they do it. Okay? So in this case, it moves incrementally, which is counterclockwise. Okay? So it fixes this one, it picks one, accepts it, and increments. Accepts it. So if this is not accepted, and it gets incremented. Anyway, what's the rest? It gets incremented. That's how it works. Is it clear how it works? Good. I'm going to stop in a couple of minutes. That's how the accept works. Poor performance of RRM. Wow. Has 50% failure. Even worse than PIM. Why is that? Why? How it can be solved? I'm giving you an example here. Imagine we got 2 by 2 2 by 2 switch. Could be 4 by 4, could be 8 by 8, could be any number. But the point here, imagine this case whereby you got 2 by 2, and of course here it has a queue that has 2 VQs, because VQ that goes there and the VQ that goes here, right? Right? Imagine that there is continuous packets coming to these queues. Okay? So we have always packets. And imagine that the pointers, they don't look at each other. Listen, this guy they don't know about, they don't even know they existed. Because they are parallel. So this pointer doesn't talk to this pointer. That's the key point of Bailey practical actually. Okay? Imagine that they are pointing to the same input. So the way this works, we said it's a round robin. So it goes here, turns here, then goes there, then ta-ta-ta-ta-ta-ta-ta. Right? Clear? If it so happens that both of them, without talking to each other, they point to the same input at the same time. So grant arbiter number, the first one, it points to that input. And this one points to that input. What happens? And we have continuous traffic. These two guys, they would always grant this. But this accepts at most 1, right? So these guys, intermittently, every time, one time they both grant 0, the other time both grant 1. Next time both grant 0, after 1, both grant 1. What happens? These guys, they will be always getting only 1 grant. Because both grants, they will either go there or either come here. They don't get spread. Is it clear? And in this scenario, it will always send both grants to the same place, which means they are wasting the grants. Because the key point is to try to spread your grants, because if there is an input receiving more than 1 grant, you know that at maximum 1 grant will be accepted. The rest are thrown away. Is it clear what I'm saying? That's exactly what happens. I don't know what I said. A slide later, my story in my head must match. Maybe you may note here, the reason for this, it is this phenomenon is known as output pointer synchronization. What does it mean by synchronization? All the output pointers, they get synchronized on the same input. Okay, that's the reason for this low performance. How can you solve it? Answering the second question. How can you solve it? Start up?
One from here, one from one.
Yes, which means the point is try to, the problem is called pointer synchronization. So the solution is try to desynchronize them. Okay, what is desynchronize them? The key point here is to try to somehow intelligently try to make these pointers point to different inputs. Okay, if you come up with an algorithm that somehow manages to move these guys such that they don't point to the same place, it's a good thing. But hopefully you do it cheaply, you don't need to pay much for it. Which means you keep these guys independent, they don't talk to each other. Because if they talk to each other, it means you are spending more time, it means you are going back to the maximum weight matching. We don't want to go back to the maximum weight matching. We want to keep it independent and parallel. because that means fast speed and easier to do. Okay? So the way to solve this is to try to make these guys somehow point always differently. And that's called output pointer desynchronization. Okay? And this is it. Remember before, it's okay, it's worth wasting time. I think I said something here. Remember what I said about this sentence? I said this is important sentence. 5 minutes ago, I said this.
Yeah.
Good. That sentence. That sentence is actually what is causing the synchronization. I will tell you why. Let's go back. Here, I'll explain this by explaining the next item. I sleep. I sleep, it says iterative sleep. Sleep meaning the pointer doesn't move, it sleeps. It's like when you are walking in the street and it's icy. You sleep, right? That's exactly what I sleep is. Maximal size, matching algorithm, I sleep call. It is a scheduler used in most vehicle switches. Cisco routers, most of them they use I sleep. Without talking, it says it's exactly, oh yeah. You see this? It says it is exactly RLM. It's exactly RLM. iSleep was proposed by a very famous person that is now full professor in Stanford. He was assistant professor when he proposed this. He sold this for 700 million to Cisco. He was pretty much a student. You know what he did? He added an if statement in RLM, in the previous algorithm. What's exactly? That if statement made him own an airplane. He has his private jet, trust me. Yeah? Now, it's not as simple as adding an if statement, of course. That if statement is very important, if statement. It's very thoughtful one. So, which means, it says, RLM, what it does? RLM grants and moves blindly. That's what RLM is doing. Round-robin scheduling gives a grant to an input and increments the pointer. That's what RLM is doing, right? Okay? Which is the case here. This guy here, what it does? It receives requests, it grants and moves. The same happens here, it grants and moves. You know what iSleep said? The guy of iSleep said, I will grant, yes, fine, I will grant, but I will not move unless my grant is accepted. Very smart. It's very simple. The update of the pointer, it's not happening at the grant moment. No, it grants and makes sure that its letter is arriving. If it doesn't, it stays there. Now, by making sure that this will not move unless this is accepted, then it desynchronizes the pointer automatically. It's making sense somehow? It sounds like I'm speaking different language. Well, I'm doing my best to convey to you the message. The details are in a paper that is called iSleep. Sorry? It's clear. Oh, very good. But still, the details are in this paper, and you got the paper on the list of papers I gave you. And iSleep, if you go on Google and see the number of citations of iSleep, you'll find it's maybe the most cited algorithm ever. Because it's very important. Okay? And the guys who propose this are the leaders in this area. Well, the leaders in the internet. Have you heard of software-defined networking, guys? Anybody of you heard of the notion of something called SDN? Nobody did? Not yet? You did? Yes? You heard about it. What is SDN? Like what?
It's a network, virtually. By the
Sorry?
software, by the software.
It's a network that
I don't exactly remember the state, but what I'm understanding is like yes, it's simulating a network, a real network, but this actually software.
Anyway, SDN is software-defined networking. This is the router. This is a very famous one. It's called the Cisco GSR. Routers, historically speaking, It's like mainframes in computers. Maybe you don't remember them. They are from the generation before you. In 1980s, 85, if you buy a computer, your choice is IBM. And they have a very complex system that's called a mainframe. That is a complex computer that everything is coming from IBM. Why? Because they have what is called vertical integration. Okay? So the computer has a complicated instruction set. The programs belong to them. It's a black box, basically. It runs DOS. What happens in the computing business comes the microprocessor era, mid-80s, early 90s. And when the microprocessor came in, a plethora of operating systems happened. Windows operating system, Linux, Mac, okay? What has happened, the instruction set in computers gets toppled up, whereby programmers, they could design their own programs, maybe their own operating system also. Okay? In networking, this did not happen. Most of the routers, they are black boxes, they are very complex pieces of equipment. They are very expensive. They are made by a couple of companies, Cisco, Juniper Networks maybe are the biggest. Huawei, the Chinese big company also. Okay? Now what is SDN? SDN is the equivalent of what happens in computing but in networking now. SDN, they are taking out the software part, the software which is the control. Couple of lectures before, for those of you, is there anybody who maintains the lectures with you? All of them? Lectures, not one. I mean plenty. Lecture number 2, if you go to lecture number 2, you will find that I mentioned about control and data path. Control path, data path. Said lecture number 2, maybe. Oh, yes, this is it. I'm sure it's somewhere here. No, this is number 1. Yes. So which lecture is this? High performance internet switches and routers.
Lecture 3.
This is it. Okay, so control, data path. There is a slide for those who can see, which is this lecture 2 or 3? I forgot.
3.
High performance router, internet switches and router. I think lecture number 3. And if you go to slide number 12, you will find what I'm talking about. This is just a parenthesis I have put down, by the way. It has nothing to do with what we are talking about today. Okay? What I'm talking about today, why I mentioned all of this, it's about iSLEEP. And I wanted to say that the guys who proposed this iSLEEP are the same guys who are proposing SDN. SDN is a big deal. Maybe we'll talk about it in one lecture in the end. Because SDN is the next step in networking. But I wanted to say that guys who bring breakthroughs are guys who think out of the box. And I will tell you about SDN later on. When these guys first talked about SDN maybe 8 years ago, nobody believed in them, everybody laughed. And they wanted to give the idea away for free. When everybody laughed at them, they moved away and made a company called Nicira Networks. These are a couple of insertions. They sold this company for 1.2 billion US 2 years ago to VMware. So if you see, there are lots of opportunities here for smart people to do things. First step, understand what the problems are, and don't be afraid of challenging the basics. Okay? Yes, please.
As you say, in this algorithm, the grant, the pointer will not be moved
unless the grant is accepted.
Okay, the question should be asking how it knows either
it's a grant was accepted or not. Basically, it's a good question still. The outputs, even in round robin, it says each grant will be notified whether the grant is accepted or not. So there is that link anyway. The link is there. Here, it's basically the pointer update happens before the accept phase or after the accept phase. Is basically timing the events. So iSLEEP does the grant does not update the pointer until after the accept phase. Round robin does the grant and updates. So it's a question of timing the update of the pointer. Because the key point in all of these algorithms, these round robin based ones, except PIM, by the way. PIM is random, so forget PIM, the one we see first. The rest of these, they are round robin based. Now, the difference between them is when do you update the pointer, how do you move the pointer. This is the difference. Whereby, again, iSleep is the first one that starts thinking smartly about how you move the pointer. Of course, after iSleep, there were again a number of plenty of algorithms. But they were timed wrongly, because the first guy is this one and was implemented in the vast majority of commercial routers. So there were plenty of better algorithms maybe than iSleep. But being the best is not enough sometimes. It could be the best and you can't make somebody win the game. Okay? So this is iSleep and this is how iSleep works. Guys, would you like, I'm really running without a stop. Would you like to have some stop? Yes. Huh? You do? If you do, please, let's have 5 minutes. If you don't, I'm happy to carry on. Good. Have 5 minutes. It's good to have a break. Let's have 5 minutes and then we will stop. And do
这一轮就会淘汰，前2轮全是博弈，这一轮只有1轮博弈。